Hi, dear audiences and fellows. I'm Shaojun Zhang from the Computer Science, the University of Sydney. Today I will present our work named DyBatch, Efficient Batching and Fair Scheduling for Deep Learning Inference on Time-Sharing Devices. First, I'd like to introduce an example on how different applications are served on a time-sharing device. So the serving system is responsible for loading and maintaining a bucket of deep neural networks, each of which is dedicated to one DL application. The DL application queries its targeting model with the streamed requests, each encompassing a number of data items. The request will invoke a deep learning inference task on the serving system. This task is an entity that holds the data items from the request, and its execution is accomplished by inference all the data items. So normally, the serving system will incorporate two mechanisms for better utilization and efficiency. The first one is batching, namely data items from multiple DL tasks are batched into a merge task for more efficient execution. The second one is fine-defined scheduling mechanism. The tasks are invoked by different applications will be scheduled to share the GPU. Namely, each of them will be allocated a time slot for execution. So here we just give a brief summary of different serving systems, namely Tensorflow serving, Clipper, and our DyBatch. We can say from the second line of this table, both Tensorflow serving and DyBatch support GPU execution, but the Clipper doesn't support GPU execution. Tensorflow serving provides a fixed batching mechanism, namely the user needs to specify a fixed batch size for the specific application. The Clipper provides an automatic coarse-grained batching mechanism, but our DyBatch will provide a fine-grained batching mechanism. Both TensorFlow serving and Clipper supports round-robin scheduling for multiple applications, and the DyBatch supports a fair scheduling mechanism. So we'd like to give the existing challenges in the current serving systems. The first challenge comes with the coarse-grained batching, namely first coming, first serving mechanism. We also present a challenge with an example. Here we run one application to serve the queries on a deep learning model. The queries are sent to the serving system in sequential, and they are batched naively, named by the coarse-grained batching mechanism. We can see from this bar chart. We can see from the blue bar here, the execution time, namely the runtime for each task, is quite small. While they are scaled, the runtime is still quite minor compared to the waiting time. So the slowdown, which is measured by the make span of the task divided by the runtime, is quite enormous, especially for the smaller task. We can say from the spikes of the dashed line here, it shows the slowdown of a really small task. So we'd like to present our DyBatch, the architecture of it is presented here. Basically, it includes the following components. The first one is a thread pool. Each thread in the pool is invoked to handle requests from one application. It will transfer data items and initiate the DLR task. Then it's the task buffer. The independent tasks from each application are queued sequentially in the buffer. And then it's the batching manager here on the right. Here it is. The batching manager will provide the normal fine-grained batching scheme to batch independent tasks in the buffer. And then it's the fair scheduler. The scheduler is responsible to choose one of the batch from the application to be served on the model server. We know that the model server holds multiple models for each application and will execute the task for real. In order to support both batching manager and fair scheduler, it's the runtime estimator, which is responsible to give an estimation of the task runtime before the real execution. So we'd like to give some details on our fine-grained batching first. Batching is formulated as a resource allocation problem as following. We know that tasks will be assigned to the batch, and the batch is represented as a virtual unit with a timestamp. In this graph, we show an example. Here we have the task stream with different sizes in each task. And for allocation 1, the tasks are batched in sequential into each of the virtual unit presented as the dashed circle. And for the allocation 2, task 3 is sliced into 2 pieces. The first piece is fed into batch 1 and the second piece is fed into the batch 2. So we can see the problem and the opportunity here. For the sequential batching, also known as the coarse-grained batching, task 3, its size is larger than the available size in the first batch. So it has to be postponed to the second batch, leaving the first one incomplete. So it's not efficient. So that's why we devise the mechanism of task slicing. Then we define an indicator to evaluate the efficiency of the allocation. So in order to reward early execution and less slowdown of tasks, the utility is defined as a reciprocal of the average slowdown. Normally, high utility indicates better allocation. We also gave some basic concept of Pareto efficiency for the task batching problem. Given all candidate allocations for the batches within one scheduling window, the optimal one with the highest utilities must be Pareto efficient. Here is another example. For allocation 2 and allocation 3, the second one is the allocation 2 only incorporates the task slicing. The other tasks are fed into each batch in sequence. For the allocation 3, task 5 is moved ahead to take the place of task 3, and task 3 is postponed to batch 2. So what's the difference here? First, we know that task 5 can be executed and finished ahead of time. And we can see also here task 3, the completion time of task 3 is limited by the completion time of the batch 2, so it doesn't make any change to the completion time of task 3. So overall, it saves the waiting time of task 5 without increasing or without sacrificing any tasks in the 2-batch window. And second, we provide the notation of envy. Within the scheduling window, a batch envies the other one only if the exchange of their allocation can result in a higher utility for them. So here we also gave an example. For allocation 1, the tasks are fed into batches in sequence. For allocation 2, task 4, 5, 6 are moved ahead to take the place of task 3. So we can see similarly, task 5 and 6 can be finished earlier, but task 3 is finished a little bit later. We provide some formulation to prove that even though task 3 is delayed, the overall or the average slowdown for all tasks are made smaller. So in other words, it's beneficial to defer task 3 to benefit smaller tasks in the next batch. For multiple application scheduling, we'd like to compare the round-robin one and fairness-based scheduling mechanisms. First, applications are assigned for execution in their respective time slot. For the round-robin one, the applications are scheduled one by one. They are not dedicated to their some specific characteristics, so it brings about some drawbacks, like the application in terms of smaller model, which always incur the shorter runtime, will be delayed a lot due to less share of the computational time. So we'd like to present the fairness-based scheduling to assign the time slot for each application in regarding to their overall share of the computational time, which is also defined as a resource utilization, which is given by the active time of the application divided by the overall clock time. We also gave some experiments on our fine-grid batching and fair scheduling. First is fine-grid batching. Here the dataset is ImageNet, and the models are ResNet 50, ResNet 152, and VGG16. Basically, we give we let each application run independently, and the queries are coming in different patterns, namely a uniform distribution or normal distribution, or Pareto distribution, or an exponential distribution. We incorporate 3 different types of batching mechanism, namely the sequential execution without batching, the coarse-grid batching, and the fine-grid batching. From each of the graph here, we can see our fine-grid batching achieves the least average slowdown among 3 mechanisms. Specifically for the uniform and exponential distribution, we can see the fine-grid batching can reduce average slowdown by up to 50%. Next, we present the experiment on fair scheduling. We this time run 3 applications simultaneously on the server. So the models are the same as what we have presented in last experiment, and this set is also same. We can see from the graphs below, the incoming pattern of the queries are like uniform, normal, and bounded Pareto. We combine the batching mechanism and scheduling mechanism, namely the coarse-grained batching with naive scheduling, the coarse-grained batching together with fair scheduling, the fine-grained batching together with naive scheduling, and the fine-grained batching together with the fair scheduling here. So we can see from the trend here, the average slowdown for the three applications can be decreased by giving fair scheduling compared to naive scheduling, and by giving fine-grained batching compared to coarse-grained batching. And our DyBatch, which is visualized by the fine-grained batching and fair scheduling here, achieves the least average slowdown. Also, we can see the bias around each point here. The bias indicates the unfairness among each applications, which is measured by the time share of the computational devices. So basically, the fair scheduling achieves really small bias, namely the unfairness is quite small. We also present some system indicators, namely the throughput and resource utilization. In the first graph here, we conducted several experiments on different batch sizes, and we can see DyBatch achieves higher throughput than TensorFlow serving. For the second graph, we can see similarly, our DyBatch achieves higher utilization under different settings of batch size, which is shown in the bracket here. So here is our conclusion. DyBatch, which incorporates fine-grained batching and fair scheduling, can improve the efficiency of serving and the utilization of the time-sharing device. It will help to improve the efficiency of clusters overall. So in the future, we would like to investigate its performance on some powerful and multiple GPU devices. Thank you for listening. It's presented by Shaojun, and if you have any question, please contact me on the email address in our author list. Thank you.